It's of course great to be at this wonderful conference and to be part of the process to honor Nati on his 60th birthday. Okay, my talk today is titled The Large D Black Hole Membrane Paradigm. Juan assigned the title. I wish he'd given me more help with the talk. Okay. These are the talk is based on these papers that I've written over the last year, ongoing projects I'm writing with students and postdocs, and builds on observation and earlier work by Emperan, Suzuki, and Tanabe, and has overlap with recent papers, some of which we'll talk about, by Emperan, Suzuki, Tanabe, and other people. Okay. So, in my experience over the course of a PhD, you learn, of course, a great deal of physics from your advisor, and much of what you learn stays with you for life. However, you also pick up some more intangible things that also stay with you for life. For instance, your interaction with your advisor shapes your taste in problems, and also molds your standards for what is considered good physics. An aspect of Nati's taste that has particularly influenced me is what I believe to be his belief in the effectiveness of simplicity. I think that Nati intuits that profound lessons are often most clearly revealed in the study of very simple situations, in simple theories, and what is sometimes unusual in our field, with the use of simple techniques. Okay, so I feel that Nati intuits that the search for the deep is often most effective in the simple, and so that's for the taste part of it. As for the standards, something that much less nebulously Nati drilled into me when I was a student was that when you can't find exact results, and sometimes when you can, even when you can, it's often useful to approximate. But approximations have very limited utility unless they're justified by a parameter. Unless there's a parameter which, when taken to infinity is 0, makes the approximation exact, and unless you can correct the approximation systematically in a parameter. Okay, so in this talk I'm going to try my best to implement this philosophy as well as this technique. Okay? So guided by these principles, in this talk I will attempt to study the incredibly simple, perhaps, but rich and beautiful equation Rmn equals 0. This is the vacuum Einstein equation, and in my opinion is the most beautiful equation written down yet by human beings. It's extremely simple. It can be written like this, but it contains a lot of physics. So I'm going to study this equation in this talk, just classical Einstein equations in a vacuum. As all of you know, this equation has in it extremely simple but extremely profound solutions. These solutions are black holes. Okay? And in this talk, what I will do is to try to use this equation, this simple, beautiful equation, to study the properties, the classical properties of these simple, beautiful, but profound objects, namely black holes. The equations that arise in the study are too difficult for me to solve, and I think are likely to be too difficult for anyone, for human beings to solve exactly. For this reason, I will take recourse in an approximation scheme, but my approximation scheme will be justified by a parameter. My parameter will be 1 over the number of space-time dimensions in which these black holes live. Okay, so let's start. Consider the metric of a d-dimensional Schwarzschild black hole. Okay? And I'm considering this metric in a slightly unfamiliar coordinate system, which is called the Kerr-Shield coordinate system. Okay? For those of you who are not familiar with this coordinate system, I apologize. A couple of simple transformations take you from the Schwarzschild coordinates to this. This coordinate system will prove very useful for me in my talk. I won't have the time to introduce it in more detail. But okay, the Schwarzschild black hole takes this form in the Kerr-Shield coordinate system. Eta mn is just the metric of flat space. And these other objects are defined as follows. is a constant one form in flat space. Okay? It's not just a one form, it's a velocity field, so it squares to -1. R is the radius, the distance from the origin in polar coordinates, where polar coordinates are set up orthogonal to So orient your time along u, and then r is the distance in polar coordinates in the space orthogonal to that time. Okay, this is a fancy equation that says that. Pmn here is the projection onto space orthogonal to time, where time is taken to be in the u direction. Okay, with these definitions, this metric here is a rewriting of the very familiar exact Schwarzschild metric. R0 is the radius, the event horizon radius of the Schwarzschild metric. Okay, now following a key observation by Emperan, Suzuki, and Tanabe, something to note about this metric is the following. Suppose you're at any r greater than r0, you hold that fixed and you take d to infinity. So you hold the ratio r by r0 fixed and take d to infinity. Then this quantity goes to infinity, so this quantity goes to 0, and your metric is just flat space. So this first simple, obvious, but important observation is that if you stay at a fixed distance away from the black hole and take d to infinity, the metric that you see is flat space. Okay? On the other hand, if you do the following, if you take r is equal to r0 into 1 plus capital R by d minus 3, and you hold capital R fixed as you take d to infinity, then this quantity doesn't go to 0 anymore. This quantity goes to e to the power capital R. Since it's the denominator, this quantity is e to the power minus capital R. And now your metric deviates from flat space. What is that saying? That's saying that if you take the large D limit and simultaneously scale where you are to be within a distance 1 by d of the black hole event horizon, that's when you see the black hole. So the black hole only affects space in a thin shell of thickness 1 by d around the event horizon in large D. This observation already makes it clear that black hole physics somehow is simpler in large D than in arbitrary D. Okay, so that's nice, it's a nice observation, but where does it take us? Now, let's do something else. Let's consider this metric here. This metric looks very similar to the metric I wrote down before, except that in this metric, u mu is no longer a constant one-form field, it's any one-form field in eta mn. Okay? It's a one-form field that is restricted to vary slowly, by which I mean its length scale of variation is 1 rather than d. Rather than, let's say, 1 by d, for instance. Okay? It's got no d in it. Okay. And rho is any function in the metric eta mn. Again, it varies, but on a length scale that's independent of d. Okay, so that's what I call slow variation. N here is the normal to the function rho. It's d rho normalized, where n is this normal vector field in flat space. So this normalization is done with the metric eta. Okay. Now I said that u and n were any old functions, that's not quite, u and rho were any old one-form and functions, that's not quite true. U squared is a velocity field, so it's always taken to be normalized to -1, and u dot n is taken to be 0. So u is a velocity field orthogonal to the normal, so in plane with the constant rho surfaces. Okay, easy enough to organize, you can come up with zillions of examples of such metrics. Okay. This is a metric. At the moment, it's not a solution to any equations. However, I want to note various properties about this metric immediately. The first is that everything I said about the metric in the previous transparency, much of what I said about the metric in the previous transparency is true of this metric as well. So suppose you look at any value of rho that is greater than 1 and held fixed as you take d to infinity, then this metric reduces to flat space. Okay? So clearly the surface rho equals 1 is a special surface in this metric. It's the surface where things start happening, where your metric starts deviating from flat space. Okay? Now, there's something a little more precise about the surface rho equals 1 in this metric. If you compute the norm of n in the metric G0 rather than in the metric eta, you find that it has the norm that it would have had in eta minus 1 by rho by d minus 3. It's a 2-line calculation to check this. What this means, in particular, is that the surface, the submanifold rho equals 1, is a null manifold of the metric G0. We will see later that the dissipative nature of the membrane equations that we will find make it very plausible, if not prove, that this submanifold is the event horizon of the spacetimes we will be interested in. So rho equals 1 is the event horizon manifold. The space-time metric deviates away from flat space only over a thickness of 1 by d around this event horizon on the outside. Now, everything I said about the outside is inverse on the inside. You go a little more than 1 by d into the inside of this event horizon, metric starts deviating from flat space a lot. You go further, it starts deviating more. Thing looks out of control. But now we know the very special thing about general relativity, and that is that the event horizon is a causal boundary. So if your interest is in predicting the future of the exterior of the event horizon, you don't care what's going on inside the event horizon. Okay? So the metric may be well out of control inside the event horizon. You don't care about it. Okay? And that's going to be my focus in my talk. So what's important to me is that outside the event horizon, my metric deviates from flat space only in a little thickness of thickness 1 by d around this event horizon manifold. Okay. Now what I want to do is to take this thing which was just a metric and make it a solution of Einstein's equations. Okay? So, as I've explained, we need to worry only about the little region of thickness 1 by d in the neighborhood of the event horizon, just focusing on the outside, because stuff far away from the event horizon takes care of itself, because flat space is an excellent solution to Einstein's equations. Okay? So, what you can show is the following. Okay, so let's start. Suppose you took this metric and you evaluated Einstein's equations on it. Because the metric is varying over length scale 1 by d, as we've seen in the neighborhood of where we're interested, you might expect that Einstein's equations evaluate to something of order d square, just because Einstein's equations are two derivative equations. Okay? And that's true if you take generic rho and u functions. But if you choose your rho and u functions to satisfy certain properties, which I'll now introduce to you, you can demonstrate that that Einstein's equations evaluate not to d squared, but to d in this membrane region when evaluated in these configurations. The properties you need to choose are the following. You need to ensure that this rho function isn't an arbitrary function, but that it obeys del squared of 1 over rho minus rho to the power d minus 3 is equal to 0. So 1 by rho to the power d minus 3 is a harmonic function in flat space. Okay? You also need to ensure that del dot u is 0, again as an equation in flat space, a divergency velocity field. Okay? Actually, you really need to ensure this only in a certain neighborhood of the horizon, but we'll find it convenient to ensure this everywhere. Okay, if these two conditions are obeyed, then it turns out you can show, and I won't try to go through the argument for why it's a simple logical argument, but we don't have the time for it. You can show that Einstein's equations, of course, not exactly obeyed, but they obeyed to one order higher than you would have expected in the large D limit. Now, this is a very good situation, because if you've got a configuration which obeys an equation to one order higher than you would have expected naively in a parameter, it means you've got a good starting point for perturbation theory. Let me explain that. Suppose I take a metric that's of the form G is G0 plus epsilon. Epsilon is a counting parameter that will be set to 1 at the end of this argument. So epsilon, it's really 1 by d. 1 by d times G1 mn. Okay, now I evaluate Rmn on this configuration. When evaluated on 0, I get what we got in the previous transparency. That was something order d. Now, when I evaluate the order epsilon piece in this, I get generically something order d squared, because Einstein's equations are two derivative. Okay? But there's an explicit 1 by d, so that's 1 by d times d squared. So this contribution here is also of order d. And therefore, you can try to choose G1 to cancel the unwanted order d part from here. Okay? and thereby get something that solves Einstein's equations in the sense that the curvatures evaluated on this configuration will not be order d, but order 1. Okay? So, yeah. Now, this procedure can be implemented. Okay, it's a long discussion for how to do this, but I'll give you just maybe one minute on this. It turns out to be convenient when you're thinking about this problem to break up to slice Einstein's equations in a particular slicing. The slices of constant rho turn out to be convenient for this problem. Okay? So think of Einstein's equations as evolution equations that evolve you forward in rho. Okay? With this convention, Einstein's equations split up into constraint equations and dynamical equations. Turns out that the dynamical equations are, I've given some details here, but I won't get into that. The dynamical equations can just be solved to find G1 given G0. You can just solve them. Okay? There's a lot to say about it. You can do it. Once you've solved the dynamical equations, though, you can solve it, and subject to the right boundary conditions and so on, the solution is unique. Okay? G1 is uniquely determined by G0, which, remember, was uniquely determined by this velocity field and the shape function, the rho function which set the shape of your event horizon. We've done this now. Okay? The dynamical equations, I've given more detail than I have the time to say. The dynamical equations can be solved to give you G1 as a function of G0, or as a function of velocity field or shape of the membrane. Once you've solved the dynamical equations, now you're stuck because you've got the constraint equations left, but no more data to fool around with to solve these constraint equations. So they just have to be solved. However, there's this wonderful thing about Einstein's equations, same thing about Maxwell's equations, where if the dynamical equations are solved everywhere, and the constraint equations are solved in one row, then they're solved everywhere. Okay? So these constraint equations are not constraints that constrain row evolution. They constrain what's happening at one row, and therefore they constrain the data, the velocity field at rho equals 1, and the shape of the rho equals 1 surface of the starting construction. And when you work that out, the constraint equations to leading order turn out to give you del dot u equals 0. In fact, that was one of the things we started with. But then another non-trivial equation. The non-trivial equation is that the projector, or P here is the projector orthogonal to velocity. All of these, the covariant derivatives in this equation, are covariant derivatives on the membrane world volume, where the membrane is viewed as a submanifold of flat space. Okay? KAB is the extrinsic curvature of that surface, viewed as a submanifold of flat space. Kappa here is the trace of the extrinsic curvature. U is the velocity field, everything else is self-evident. Okay, what you get here is you get these equations. Okay, it's a set of vector equations on the membrane world volume that you need to satisfy in order for this perturbative procedure to be consistent. Now, from the point of view of perturbation theory, you might think of these vector equations as integrability constraints. Unless this is satisfied, your starting point wasn't near a true solution of Einstein's equations, so you couldn't proceed. But remember that all these derivatives include derivatives in time. So what this really is a bunch of dynamical equations. It's an equation that's deciding the dynamics of the event horizon surface and the velocity fields on the event horizon surface. Okay? What's really interesting here is the counting of the business. You see, it turns out that there are exactly as many equations as variables in your problem. Let's count. The variables in the problem were the shape of the event horizon, that's one function, and a velocity field in the event horizon, that's d minus 1 functions. Okay? Actually, that's d minus 2 functions, because the velocity field, the velocity field was a vector field in d minus 1 dimensions, but it was also a velocity field. So it's where u squared equals minus 1. Okay? So that the total number of equations was d minus 2 plus 1, so that's total number of variables was d minus 2 plus 1, so that's d minus 1. Now let's count the number of equations. We've got this equation here, so that's 1. And this equation here that looks like d minus 1 because it's a vector equation on a d minus 1 dimensional manifold, but it's the projector here. So it projects orthogonal to one of the directions. It's actually d minus 2 equations. So we've got d minus 2 plus 1. So we've got as many equations as variables. This is the key point. The key point is that the integrability constraints of the procedure are as many in number as the free functions you had to start up the procedure. The free functions were functions of time. That was the alarm signal that we were doing something wrong, because you never in physics have free functions of time. The role of physics is to start the given time, tell you what happens later. These equations tell you don't have free functions of time. Initial conditions determine the future. Okay? So this procedure gives you a set of dynamical equations for the variables, the true slow variables of the problem, the velocity function and the shape of the horizon. Okay, I've said this here. Now, the equations that you get here are reminiscent of the equations of hydrodynamics. Anyone familiar with hydrodynamics will recognize this as a convective type term and this as a viscosity type term. But these are equations that are equations of hydrodynamics not on a fixed background manifold, which is where hydrodynamics is most usually studied, but on a fluctuating background manifold. And that gives much of the fun of these equations. So it's hydrodynamics with a twist. Okay. Fine. I had some comments here on the old membrane paradigm, which we'll skip. I made these comments in my strings talk, which I'm sorry has substantial overlap with this talk, but for those of you who were there. But okay. I explained how you could get the first order equations of motion. Turns out that this procedure can be iterated and continued to arbitrarily high order in 1 by d. We've explicitly implemented the iteration to the next order in 1 by d. And the equation that was del dot u is equal to 0 turns into del dot u is equal to something, which is 2 orders in 1 by d suppressed. In order to understand the orders in 1 by d, you need to understand what orders various terms have, which I'll tell you if there are questions, but I'll avoid otherwise. And this dynamical equation that was here, that was only the first line on the previous transparency, gets modified by this to this plus a correction term. So all that happens is that your equations of motion get a 1 by d expansion. The structure remains unchanged order by order in 1 by d. Okay, everything I said has a straightforward generalization to adding charge. You can start not with the Schwarzschild solution, but the Schwarzschild-Reisner-Nordstorm solution. Then the data of your perturbative parameter includes not just a velocity function and shape function, but also a charge function on the event horizon. And because you've got one more function, it wouldn't work unless you got one more equation. Turns out you get one more equation. This equation is sort of like, this is like the charge diffusion equation in hydrodynamics. Okay, it has many similarities to that. And the fact that you get one more equation along with one more variable tells you continue to have a good initial value problem. Okay, now that we've got these equations, we can try to do something with them. So the first thing there are many things we'll end up doing if I get the time in this talk, but the first thing I'm going to do is to take the simplest solution of these equations, which is just a round sphere, and to linearize the equations around this round sphere. When you do that, I do this for the general charged case. When you do that, you find a bunch of frequencies. You find the frequency spectrum of the problem. Okay? And these equations are easy to solve, and you get these frequencies. There are many things to note about these, but I'll just point out a couple. The first one that's really important is to note all these I's here. If you study the spectrum of frequencies in detail, with a little attention, you will see that all of these frequencies correspond to damped motions, except for a few exceptional zero modes, which have no I's there, but you never get I's with the wrong sign. You get some zero modes. Every time you get a zero mode, you can identify it. For instance, there's a zero mode corresponding to translations of the black hole. There's a zero mode corresponding to scaling up the black hole. There's a zero mode corresponding to setting the black hole rotating. Okay? But there's nothing else. So every zero mode is identifiable. Every other mode is damped. Notice that the time scales for damping are just order 1. This, by the way, is different from hydrodynamics because the first order equations that we got, the lowest order equations, are already dissipative. Unlike in hydrodynamics, where perfect fluid hydrodynamics is non-dissipative, and to see dissipation, you need to go to the next order. These equations are like those of hydrodynamics, but because of because of the fact that they're not on a constant manifold, somehow they're more dissipative than hydrodynamics. Oh, okay. Now, the other thing about these relations is that you can compare them with the spectrum of quasi-normal modes that you can independently compute just using gravity. about Schwarzschild black holes at large D. In fact, our interest in this problem was sparked by the fact that Empran, Suzuki, and Tanabe did this calculation year and a half ago, and they found a nice spectrum. The spectrum was this spectrum plus a lot of other stuff, but the other stuff was all very heavy. Both the real and the imaginary parts of the other stuff all scaled like D. See, now they had a spectrum with a gap with light stuff, and we exactly reproduce all their light stuff, but they also had some heavy stuff. This explains what we are doing in their language. Whenever in physics you've got a spectrum with a gap, you can try to integrate out the heavy stuff to get an effective nonlinear theory of the light stuff. And that's what our membrane equations are. Our membrane equations are the non-effective nonlinear equations of motion of the light quasi-normal modes of Empran, Suzuki, and Tanabe. Okay, now let's do another calculation. Instead of starting with this round sphere, let's take a simple generalization of the round sphere. That is, continue to work with the configuration that has trivial velocity u is minus dt. But look at the shape as S, a sphere which is a smaller dimensional sphere, and soak up the additional dimensions in just flat RP. That also continues to solve the equations. Now, the earlier solution was a solution dual to black hole. This solution is dual to what people sometimes call black branes. The most familiar example is the case p equals 1, in which case you've got a sphere times a line, that's called a black string. Black strings were made famous, at least for me, by Gregorry and Laflamme when they discovered more than 20 years ago that these solutions in general relativity are always unstable. Okay? So the next thing you can try to do is to try to see if you can see and understand the Gregorry-Laflamme instability in this membrane picture. Okay, so you start with this solution. Turns out the Gregorry-Laflamme instability maintains the isometry of the sphere. So we look at membrane fluctuations that maintain the isometry of the sphere and just linearize around this configuration. Of course, if you don't turn on momentum in the extra black string directions or the black brane directions, you're back to the old problem. But when you do turn on momentum, something changes. And it turns out that you find a particular mode whose frequency is I times minus kappa by square root n minus kappa squared by n, where kappa is the momentum along the brane and n is d minus 3. You can think of n as d to this order. Okay? Now, the signs are such that, this should have been a plus, I'm sorry. The signs, there was a plus here but a minus here, sorry about that. The signs are such that this guy represents an instability until this overwhelms this. Okay? So this represents an instability for k smaller than square root n. Okay? This is in agreement with Gregorry-Laflamme's results if you specialize them to large D. Notice that at large D, the Gregorry-Laflamme instability persists down to a very small length scale, a length scale of order square root of d. The factor of square root d or square root n in this frequency suggests that everything interesting in this physics is happening at a length scale square root of d. Okay, so, and if you look at the eigen modes, which I haven't shown you, it suggests that the fluctuations of the radius are happening on a length scale 1 by d. Okay, so motivated by this fact, you can move to scaled coordinates for flat space. It's minus dt squared plus dy squared. These are the membrane coordinates, the yi squares. No, sorry. These are the membrane coordinates, dxa by n. So you scale the membrane coordinates so that order 1 by square root d is now order 1 in these new coordinates. And you work around a given radius, I've taken that to be 1, and scale fluctuations so that fluctuations of this y coordinate are fluctuations of the radius of order 1 by d. Okay? This is just a new set of coordinates for flat space. And then take the membrane equations which are covariant and apply them in these coordinates, assume everything on varies on length scale 1 in the new coordinates, and then take d to infinity. Okay? When you do that, you get a set of simplified membrane equations, which after a particular field redefinition becomes even simpler. They become not just simple, but they become identical to a set of equations obtained earlier by Empran, Suzuki, and Tanabe, who were trying independently to use large D methods to study the Gregorry-Laflamme instability. So, previous to this stuff is in a paper we put out earlier this week. Previous to this, it was a bit unclear about what the relationship between these two different methods of trying to understand large D were. Now it becomes clear the equations of Empran, Suzuki, and Tanabe are just a particular scaling limit of our membrane equations. The scaling limit, for those who followed fluid gravity, is very similar to the scaling limit that you have to do to start with the non-relativistic Navier-Stokes equations and go to the, start with the relativistic Navier-Stokes equations, go to the non-relativistic Navier-Stokes equations. Very similar kind of scaling limit. So these equations are sort of analogous to the non-relativistic Navier-Stokes equations. Okay, great. Now, with these equations, Empron, Suzuki, and Tanabe, using numerics, were able to solve for the time evolution of this Gregorry-Laflamme mode and show that it stabilizes, that the nonlinearities in this thing stabilize that instability into wiggly black string, in agreement with the general expectation that the Gregorry-Laflamme instability is sort of boring in dimensions d greater than equal to 14, because the endpoint's a wiggly black string, but interesting in d 13 or less when it pinches off and presumably leads to a naked singularity. Okay, let's move on. Okay, I've told you how to reword the dynamical equations of black holes in terms of the dynamical equations of a membrane. Oh, by the way, I should have said that there's a nice set of words you can put to this instability here. The words is the Rayleigh instability. You know, Rayleigh, very long ago, realized that long tubes of fluids were unstable. And there was an instability there to droplet formation, or at least to its tendency of droplet formation. So, viewing this in the membrane picture really turns the Gregorry-Laflamme instability into the Rayleigh instability. Okay, with Rayleigh had different equations of motion, but it's very similar. Okay, fine. Great. So I've explained to you how you can take the dynamical equations of black holes and, in a precise sense, I want to emphasize, in a particular parameter regime, reword them as the equations of hydrodynamics on a membrane. Okay? And that's all very nice, but suppose you were a large D observer doing a LIGO type experiment, which we'll come back to at the end if I have the time, and you wanted to know what was happening there. You know, the way people outside know what's happening is by measuring gravitational radiation. So the next natural question to answer is, when your membrane is undergoing a particular motion, what is the effect of gravitational radiation? How does someone outside see it? And that's what we're now going to try to answer very quickly. Okay. This question is not too difficult to answer once you realize various things. I haven't even shown it to you because it's too complicated to show on a slide. It's too little time. But along with these equations of motion, our papers also have a metric. Okay? When these equations of motion are satisfied, when these equations of motion are satisfied, okay, whatever. When these equations of motion are satisfied, oh no. The metric that I wrote down for you initially, namely this metric here, gets corrected to first order and second order. That was the role of the dynamical equations. And we have explicit forms of the corrections. Okay? Now you can ask, when are these correction forms reliable? And it turns out that the corrections to those metrics are reliable in this region. They're reliable provided this rho function, I'm sorry. This should have been rho minus 1. This should have been rho minus 1 here. Provided the difference between rho and 1, okay, is much, much less than 1. It's not large in units of 1. On the other hand, I've already explained to you that the metric here becomes more or less identical to flat space once rho minus 1 is much larger than 1 by d. Okay? So we've got this regime, regime of space when rho is much, much larger than 1 by d but much, much less than 1, where two different approximation schemes overlap. The first one, when rho minus 1, this should have been, when rho minus 1 is much, much less than 1, is our construction of the metric. The second one, when rho minus 1 is much, much greater than 1 by d, is the linearized solution to Einstein's equations. Okay? So we cannot use our metric directly to read off the radiation field because our metric is not reliable for arbitrarily large rho. But what we can do is to read off what linearized solution of Einstein's equations our metric corresponds to in this overlap region, and then continue that solution to infinity using linearized Einstein equations. That's correct procedure. Turns out there's an elegant way to implement this. Turns out there's an elegant way to implement this. It turns out that the effective implementation can be worded as follows. 5 minutes, yes. You assign a certain stress tensor to the membrane. Okay? The stress tensor is determined by a solution of your membrane equations. I don't have the time to explain exactly how that's done. There's some nice counter term kind of stuff you can do, but it doesn't matter. You assign a certain stress tensor to your membrane. That stress, there's a formula that you can derive for the stress tensor in terms of shape and velocity fields. And then determine the gravitational radiation by convoluting that stress tensor with a retarded Green's function. The stress tensor is just the source. Okay, the stress tensor lives on the membrane. Okay. Now, explicitly when you do the calculation for the stress tensor, I've given the answer to leading non-trivial order in 1 by d. You find this value of the stress tensor. Okay. Now, similarly, you can find a charge current on the membrane, which you couple to a retarded Green's function to get the radiation field for charge. Now, you see, it's a basic property of stress tensors or charge currents that they give nonsensical, they give meaningless results. They give results that are not gauge invariant for radiation unless they're conserved. So if everything I've said is correct, then the stress tensor had better be conserved and the charge current had better be conserved. But you can just do the calculation. You can just check whether the stress tensor and the charge current are conserved or not. And when you do, when you do that, let me try to fix. Okay. Oh, thank you. Okay. Okay. So when you do that, you find that the stress tensor and charge current are conserved, but in fact, the statement of conservation is just a restatement of the equations of motion on the membrane. So the best way to talk about the equations of motion on the membrane is just to talk about the stress tensor and the charge current, and then assert that they conserve. That gives you the dynamics of the membrane. Okay. Now, the membrane stress tensor and charge currents that I've talked about in this transparency are not small. For velocity and shape functions of order 1, turns out that they are order d. Okay, so in fact quite large. Okay, and this might then suggest, from what I've said, that this order d stress tensor and charge current would lead to a lot of radiation because you just have to couple to a Green's function and let it radiate. And that would lead you to suspect that everything I've said was wrong, because I've got local equations of motion on a membrane, order by order in 1 by d to every order in the 1 by d expansion. But that seems inconsistent with interactions mediated by radiation, which is clearly non-local. Okay? The way out of this conundrum turns out to be interesting. It depends on a simple kinematical fact about Green's functions at large d. Turns out Green's functions at large d, and I didn't know about this a few months ago, and if you don't know about it, it's quite interesting, are very sharply, quite strange. Okay? In order to explain this, I'm just going to lead you through a quick analysis of the scalar Green's function at large d. Consider the Green's function, I'm dealing, to be concrete, with the retarded Green's function. None of it really matters. The retarded Green's function at large d, and I work in a mixed representation where I Fourier transform in time, but work in position, space, and space. Turns out to be convenient for seeing the properties of this function. Okay? So the Fourier transform in time, but position, space, and space, away from the origin, obeys the equation del squared g is equal to 0. By making a change of variables, you can transform that equation to a Schrodinger type equation by getting rid of the first derivative term. What's interesting about the Schrodinger type equation is that it's the Schrodinger equation of a particle moving in a potential, and this potential is a positive potential of order d squared. It's a potential like d squared by r squared, d squared by 4r squared. You're moving in a potential that scales like d, but with an energy that scales like 1. Okay? So, unless r becomes very large, the solutions of interest are tunneling type solutions through this potential. It's only when r is of order d by 2, or d by 2 omega actually, that you start, you have the propagating solutions of the Schrodinger equation. Now we're right. Okay. What this 2 minutes. Okay. What this turns out to mean is the following. It turns out to mean that if you've got a source here and you start radiating because of that, the radiation has to tunnel through a huge barrier. The response becomes very small by the time it finishes tunneling, and then it propagates into radiation. Turns out to give you a suppression that's of order 1 by d to the power d. What we're seeing here is decoupling. In this situation, we've got two kinds of light modes. The light quasi-normal modes localized around the black hole, and light radiation modes outside. And this potential barrier is leading to decoupling, very much like Juan's decoupling for D3 branes, except that the thing that's governing this decoupling here is not low energies, but large d, or you can say it in many ways. Okay? By the way, this decoupling works the other way as well. If you shine something on the black hole, it has to go through this large potential barrier before it affects the black hole. So the effect of an order 1 radiation field on the black hole is suppressed at order 1 by d to the power d. So we've got this almost decoupled sector. Light radiation and these light black hole modes hardly talk to each other. But the first 1 by d to the d coefficient of the radiation and all this coupling is completely computable, and we can compute it. Okay, I don't have the time to say much more. There's an entropy current on these black holes that you can use Hawking's area increase theorem to determine an entropy current on the black hole, prove abstractly that its divergence is positive definite, and then check explicitly using the membrane equations that the entropy current of the black hole is locally positive definite, so that membrane motions always create and never destroy entropy in accordance with the second law of thermodynamics, but a local form of the second law of thermodynamics. You can construct interesting classes of stationary black hole solutions which have charge and rotation, just sort of elliptical membranes that are rotating around. I don't have the time to talk about that. Conclusions. Okay, so what? We've demonstrated that the near-horizon geometry of charged and uncharged black holes decouples from the asymptotic infinity at large d. At the classical level, the decoupled theory is governed by a set of equations that describe the propagation of a membrane in flat space. The degrees of freedom of this membrane are its shape and a velocity and a charge density field. The membrane carries a conserved stress tensor and charge current, whose explicit form we've determined at low orders. Membrane equations of motion are simply the statement of conservation of these currents that appear to define a well-posed non-gravitational initial value problem. Radiation is the failure of decoupling and occurs at order 1 by d to the power d. The explicit form of radiation is obtained by coupling to a charge current and stress tensor, which we know. And there are various potential extensions. In the last 10 seconds, I'll say that you can use this formulation to try to study a very interesting black hole. This is a toy model of real black hole physics. You can use it to study very interesting black hole motions like black hole collisions. Almost. You see, the black hole collision involves the two black holes coming together where nothing happens in a membrane picture, and then something funny happening, and then the membranes open out. After that, once the opening out is more than 1 by d, we can use our membrane equations. We haven't yet developed the procedure for understanding this opening out, which I think is a doable problem. We haven't yet done it. If we can do that, then we've got a set of equations that allow, in this nice 1 by d expansion, allow you to study very interesting things like black hole motions, and to understand, for instance, that black hole motions will never produce naked singularities, because it'll be obvious that it will never happen, and so on. So it's a nice toy model to understand structural features of general relativity. What else it's good for? Well, I have speculations, but I don't yet know. Thank you.
Questions? Nadi?
So you mentioned examples where the qualitative behavior is different in 4 dimensions.
Yes.
And there are examples where it's expected to be correct. Do you know a priori whether you should or should not trust this, the qualitative behavior that the large...
For any particular dynamical process?
That's right.
I don't really know. All I know is really experimental evidence. I can tell you that what we did is look at the spectrum of light quasi-normal modes. There are these vector quasi-normal modes which are very easy to track. You look at the spectrum of light quasi-normal modes that we've got in our calculations, you put d equals 4 in the answers, and then you compare them with the first few things that people compute numerically in d equals 4, it agrees to within 10%. So, that part seems okay. But of course, as you said, Gregorry Laflamme is qualitatively different. I don't know what the general rules are.